Hey everyone, welcome back to your calculus videos here. Now that we're in second semester, we're going to kind of get into the second big chunk of calculus content. So really all first semester we were focused on derivatives and their applications, and this semester we're going to be working a lot with what we call integrals. And so this video is going to kind of give you an introduction in what integrals are and how we can start to calculate them. So just as a quick review, last semester we spent the majority of our time learning how to find the slopes of functions at one point. Right? So really what we were talking about there was the slope of the tangent line, and we called these slopes derivatives. Okay, and we learned a whole bunch of applications for these derivatives. So we had the slopes of tangent lines. We talked about position, velocity, and acceleration. We used them to sketch graphs of functions. We did optimization and related rates problems. And then we could make guarantees about either values of functions or the slopes of functions using those big theorems. If you remember, the extreme value theorem, the intermediate value theorem, and the mean value theorem. So that was all last semester, again, really focused on those derivatives. So this semester, we're going to be learning how to find the areas that are trapped between the graph of a function and, this should say and, the x-axis. Okay, and we're going to be using these areas in application questions later on. And so integrals are what allow us to find these areas. Again, we're talking about the area trapped between the graph of a function and the x-axis. So first we're going to look at the notation for these integrals. So the first thing I need to notice is whenever I see this symbol here, this kind of long S-looking thing, that's our symbol for an integral. And that's telling us that we're going to find the area. Now remember, we said up front that we're always, or at the top of the page, that we're finding the area trapped between the graph of a function and the x-axis. So when we see this notation, really we're finding the area that's trapped between this function and the x-axis. Okay. Now this A and B, really that tells us where to stop, or excuse me, to start and stop. So we call those the limits of integration. And again, this is just starting x value and our stop here at x equals b. And again, we call those the limits of integration. Now, the only thing that I really want to emphasize notation-wise here is you'll notice at the beginning of my integral, I always start with the integral symbol, and I always end with the dx. So notation-wise, we have to make sure we're always ending with that dx. So you can kind of think of this as a set of parentheses. The integral sign is going to open that up, and the dx is to close it at the end. So you want to make sure you're always including that notation at the end of your integral. So let's look at an example of what this might look like in a problem. So my example says the graph of f of x equals the square root of 9 minus x squared is given. Notice that's the semicircle here with radius 3. And I want us to really pay attention, make sure we recognize this function because we're going to see these equations of semicircles over and over again, so you definitely want to recognize what they look like. So now it says, show what it means to find the integral from -2 to 3 of the square root of 9 minus x squared. So here's what we said. We said the integral means that we're finding an area. We're finding the area trapped between this curve, so between this semicircle and the x-axis. And now if we look, it says from -2. So I have from -2 here to 3, and my 3 is here. So what that tells me is I'm going to start at -2, Again, I'm finding the area tracked between that curve and the x-axis between -2 and 3. So if I were to calculate that integral, that's what I would be finding, is the area kind of shaded in green there. And throughout the chapter, we're going to learn a lot of different ways that we can calculate that integral. All right, last thing before we actually go and calculate the values of these integrals is this note down at the bottom of the page. Let's see here. Okay, so it says, note, when areas are above the x-axis, they have positive y values, they are considered positive. So those areas are going to be positive areas. So if I were looking here, right, I notice here the area trapped between that curve and the x-axis is positive, and this one would be positive as well. So the values of those integrals would be positive. On the other hand, when the areas are below the x-axis, they have negative y values, they're considered negative. So we're going to want to be really careful when we start calculating these integrals to pay attention to where those areas are located relative to that x-axis, whether they're above or below. Okay, so now we've got the basics of what we need to be able to go ahead and calculate some integrals. And today we're really just going to be using geometry to find the values of these integrals. So we have to know our basic geometry formulas. Typically we'll be using rectangles, triangles, semicircles, and trapezoids to find the value of these integrals. Okay, so this first example, it gives us the graph of f of x, and it says to use the graph to evaluate the following integrals. So my first one is from -3 to 0 of f of x dx. So -3, I've got over here. And what I'm noticing is from -3 to -2, that's above, so I'm expecting that's going to be a positive area. And then, just to kind of keep this clear here, from -2 to 0, I drop below the x-axis. So I know that's going to be a negative. So I have to keep that in mind when I'm calculating this area. So let's see what we get. I'm going to use colors here to kind of differentiate between the positive and the negative area. So this is going to be, my first shape here is a triangle. So I know that's 1/2 base times height. So I have 1/2. The base length is just 1 unit. And then the height is just 1 as well. So that's my positive area. Now, instead of this area, instead of adding it, I'm going to subtract it because it's below. So I have a minus now. Again, it's a triangle, so I have 1/2 times the base now is 2 units. And let's see, the height of that triangle is 2 units as well. So now I've got all the pieces, and we just do that calculation to find the area. So I have 1/2 minus, let's see, 2 times 2 is 4, divided by 2 is 2. So I have 1/2 minus 4/2, so I have -3 over 2 for the area. And again, that negative is just telling me that there's more area below the x-axis than above, which I can see visually, so that negative area makes sense to me. All right, let's look at another one. In example 2, I've got the same graph, but now I'm looking at the area between 0 and 4. So between 0 and 4, again, I'm using blue because this is below. And actually, it's below the whole way, so I just have negative areas. Now, this one's a little bit interesting because when I first look at this, I don't know a geometry formula for a shape that looks like this with this curved edge. But what I do know is if I could take the area of this whole rectangle, right, with base 4 and height 2, and I could subtract out that semicircle, then I'd have the area for this, or the value of the area for that shaded region. So let's see what that would look like. So again, I could take the whole rectangle. So the rectangle is 4 times 2. And now I'm going to subtract out this semicircle. So I have pi. Looks like the radius of my semicircle is 2. So I have times 2 squared. And this is just a semicircle. So I've got it over 2. So let's see what I have. I have 8 minus 2 pi. And actually, I have to be careful here. This is below the x-axis, so this whole quantity should be negative. So now, if I do this, I get the area, which is negative 8 plus 2 pi. So that's the exact area between 0 and 4. All right, last one here. Now I'm looking for the area between this curve and the x-axis from negative 3. So I have positive, and then I want all the way to 4. So I'm going to keep going, and I'm just doing this blue again because I'm below. All right, so I want to figure out the value of that integral. Well, the nice thing here is I can really reuse what I've already done. We already calculated the value from negative 3, to 0. And we knew that was negative 3 halves. So that covers from negative 3 to 0. We also did from 0 to 4. Now, this was a negative, and I have to remember I'm subtracting this as well. Okay, so when I do this, we already found this area, this negative area, so I'm adding the negative area. So I'm going to add a negative 8 plus 2 pi. So now I can add those together. I've got negative 3 halves. To make this easier, I'm going to make this minus 16 halves. And then I have plus 2 pi. So the total area there then is negative 19 halves plus 2 pi. Okay, so that's the first type we're going to be looking at, where they've given you the graph and you just have to apply those geometry formulas to find the value of the integral. So the last few we're going to do here now, you have not been given the graph. You're going to have to come up with the graph first, but then still using those geometry formulas. Okay, so we're going to sketch a graph of the function to help us evaluate the integral. So right away here, we're seeing that formula that I said we all need to be really familiar with. When I see this, I know automatically that I have a semicircle, and the radius is 2, so the square root of 4 there. So I'm going to sketch this out. I have a semicircle centered at the origin, and the radius is 2. So it's not perfect, but not too bad. And so I'm integrating from negative 2 to positive 2. So I'm finding the total area between that semicircle and the x-axis. And again, it's above the x-axis, so I expect this value to be positive. So I'm just going to use my area for a circle. So I have pi times, we said the radius was 2, so pi r squared. It's a semicircle, so it's over 2, and I get an area of 2 pi. Okay, and number 2, here I have a constant function, right? This is really telling us that our function here is y equals 3. So a nice, easy one to graph. So I just have my line here. There we go. And I'm integrating here from negative 4 to negative 1. Okay, again, a nice, easy shape to work with. I'm above the x-axis, so my area is positive. So now I just have a rectangle. The base of that I can see is 3 units wide. My height is 3, and so my area is 9. Okay, my next one is just a little bit trickier. You can see I have a piecewise function here. So let's see what we've got. It says f of x equals 2 for x less than or equal to 2. So again, I'm constant. It's closed at 2. So I've got a point here. And I've got that constant function. And then from there, my function is y equals x for x greater than 2. So basically just got a slope rise over run, 1 over 1. So it's going to look like this. I'm going to put one more point on here. So it looks something like this. Okay, now we're integrating from negative 1. So let me put that on here. So from negative 1 all the way up to 4. So I'm going to kind of do this in two colors. The whole area is going to be positive because everything's above, but I'm kind of seeing this break out as a rectangle here. And then let's see, I've got here, if I kind of look at it sideways, I'm seeing a trapezoid kind of on its side. So I'm going to use two formulas here. So for my first piece, I'm going to have just the rectangle base times height. So in this case, my base is 3. And my height is 2. And then I'm going to add, now if you don't remember, I'm going to make a note here. The area of a trapezoid, which is actually going to be super important this chapter, is going to be the height over 2 times base 1 plus base 2. And remember, those bases are the parallel sides. And the height is the distance between the parallel sides. So in this case, my height is 2, so I have 2 over 2. Now my one parallel side has a length of 2. On this end, this is 4. So now I've got the two pieces that are going to make up that area. So I have 6 plus 6, and I get an area of 12. So making good quality graphs is going to be really helpful here. If you have a messy graph, it's really kind of hard to determine what the function values are and sometimes even what shapes you should be using. Now the last one, this function actually comes up quite a bit in calculus, so I want you guys to be familiar with it. Whenever we see this absolute value of x over x, it's going to look like this. So for positive x values, they're going to be a value of 1. For negative x values, they're going to have a y value of negative 1. So again, this is just a function that I'd like you to have kind of memorized in your head because it does come up. And if you know what the function looks like, it's going to make you more successful when this comes up, for example, on a no calculator question. So now let's see. I'm integrating from negative 1 over to 2. And here we see we've got our negative area come back here because I'm below the x-axis. And then from 0 to 2, we go back to positive. So when I'm finding this area below the x-axis, I'm going to make sure that's negative. I have a rectangle here. Base and height are both 1. And then I'm going to add this rectangle. So the base here is 2. Height is 1. So I get negative 1 plus 2, which is equal to 1. So that's what you'll really be focusing on first, is just using geometry to find the values of these integrals. So what I want you to really take away from today is just recognizing the notation, knowing that the integral is just telling us to find the area between the curve and the x-axis, and then knowing that those areas below the x-axis are negative, above is positive. So like I said, we're just focused on these geometry formulas for now. As we go through the chapter, you'll be learning other methods to evaluate these integrals. So that's it for today. I'll see you back in class.